Back in 1956, a machine didn't just solve a complicated math problem faster than a human.
Right.
It actually found a more beautiful, more elegant path to the truth than two of the greatest mathematical minds of the 20th century. Welcome to Deep Dive.
It really is an incredible story. I mean, we're looking at a field that sits right at this crazy intersection of pure mathematics, philosophy, and artificial intelligence.
Exactly. And our mission today is to give you, the listener, the ultimate shortcut to understanding this foundational, almost science fiction level concept in computer science, which is automated reasoning.
Yeah, it's a heavy topic, but we're going to break it down.
We really are. And just to give you a sense of our roadmap, we are pulling from a really comprehensive Wikipedia article on automated reasoning today, along with several of its deep cut reference materials.
Some really fascinating sources in there.
Oh, for sure. And for you listening, here is exactly why you need to care about this. We are living in a moment right now where everyone is using these AI chatbots, and, well, we all know they hallucinate, right?
Oh, constantly. Yeah, they just constantly make things up.
Right. So understanding automated reasoning is the key to knowing how we are actually teaching machines, not just to guess the next word in a sentence, but to, actually think, deduce, and verify truths with absolute certainty.
It's the antidote to the hallucination problem.
Exactly. Okay, so let's unpack this. We need to set the foundation first. What exactly is this field even trying to achieve?
Well, the primary goal of automated reasoning is to basically build computer programs that allow machines to reason completely automatically, or, at least as close to completely as mechanically possible.
So we're not just talking about a chatbot that sounds smart.
No, not at all. We're talking about a machine that deduces what is mathematically and logically true. The most developed areas here are automated theorem, proving where the machine actually discovers a proof on its own, and automated proof checking.
And proof checking is where the human does the work first.
Exactly. A human provides the reasoning, and the machine rigorously verifies that absolutely no logical laws were broken.
Okay, so to do that, to actually automate reasoning, we have to define what perfect reasoning looks like, right? Which means we have to step completely away from how the human brain actually operates.
Right, because human reasoning is just incredibly messy. It relies heavily on intuition.
Yeah.
A human mathematician will just, skip a dozen minor logical steps in a proof because a connection just feels right, or it looks obvious based on their past experience.
When I was reading the sources for this, it made me think of walking across a frozen lake.
Oh, interesting. How so?
Well, human intuition is like looking at the ice, seeing it look solid enough, and just walk it across. You take a few steps, you don't fall in, so you just assume the whole lake is safe.
Right. You extrapolate.
Yeah. But formal logic, on the other hand, is like pausing to check the structural integrity of every single individual ice crystal before you are willing to move even an inch.
That is a great analogy. And what's fascinating here is that a formal proof requires exactly that microscopic level of scrutiny.
It's relentless.
It really is. In a formal proof, every single logical inference has to be traced all the way back to the fundamental axioms of mathematics. You absolutely cannot skip steps.
No intuitive leaps allowed.
Zero. You cannot appeal to intuition. Even if translating a specific, intuitive leap into formal logic would be totally routine and boring for a human mathematician, the machine demands the intermediate steps.
It forces you to show your work.
Exactly, because by removing human intuition entirely, a formal proof strips away the exact places where logical errors like to hide.
That makes total sense.
Yeah.
But logic isn't always just proving that 2 + 2 is 4, right? Life and human thought involve a lot of gray areas. Does automated reasoning only deal with rigid black and white math?
No, it goes much deeper than that, actually. The field also tackles how to reason by analogy. For instance, it works with induction, which is drawing a general rule from specific examples.
Okay.
And also abduction.
Abduction, like an alien abduction.
No. Logical abduction. It's essentially forming the most likely explanation for a set of observations, like a doctor diagnosing a patient based on a list of symptoms,
Oh, I see.
Yeah, and the sources also highlight something called non-monotonic reasoning.
Okay, non-monotonic. I'm going to need you to break that down for me.
Sure. So in classical logic, once you prove something is true, it stays true forever. Adding new information doesn't change it. That's monotonic.
Right.
Non-monotonic reasoning is closer to real life. It's when you might draw a logical conclusion, but then you learn a new piece of information that actually forces you to retract that earlier conclusion.
So you basically change your mind based on new evidence.
Right, exactly. And a brilliant example of this from the reference materials is John Pollock's Oscar system.
Oscar.
Yeah, Oscar is an automated argumentation system. So instead of just proving a rigid math theorem, it applies constraints of minimality and consistency to literally argue with itself.
Wait, it argues with itself.
Yeah. It builds what's called a defeasible argument. Defeasible meaning, an argument that can be defeated. The system generates a claim, and then it systematically searches its own database for a counterexample to destroy its own claim.
That's wild.
It acts as both the prosecution and the defense, weighing evidence under uncertain conditions.
Honestly, that sounds computationally exhausting. I mean, checking every single mathematical ice crystal or having a machine constantly prosecute and defend its own thoughts.
What's a massive amount of processing?
It really makes me wonder what forced early computer scientists to even attempt this. Did they just, get tired of doing manual math?
Well, sort of, yeah. The sheer physical limitation of the human brain to hold massive logical structures without making a single mistake was a huge driver.
That makes sense.
But the actual birth of the field is heavily debated. Some historians point back to Martin Davis in 1954. He implemented a concept called Pressburger's decision procedure, and his program successfully proved that the sum of two even numbers is even.
Okay, 1954.
Right, but others argue the field really crystallized a few years later, at this really famous Cornell summer meeting in 1957 that gathered logicians and computer scientists together.
The project that really caught my eye right in that same window was the Logic Theorist program from 1956.
Oh yes, a classic.
The creators, Alan Newell, Cliff Shaw, and Herbert Simon, they pointed their machine at this massive book called the Principia Mathematica. What was the deal with that specific book?
Well, the Principia Mathematica was a monumental multi-volume masterwork written between 1910 and 1913 by Alfred North Whitehead and Bertrand Russell.
Okay.
Their whole goal was to derive all mathematical truths purely in terms of symbolic logic. It was widely considered the absolute Mount Everest of formal logic.
So naturally, you point the new computer Mount Everest.
Exactly. So Newell, Shaw, and Simon fed 52 theorems from Chapter 2 of this absolute beast of a book into their Logic Theorist program.
And the machine proved 38 of them.
It did.
But here's the part that I just couldn't believe. The logic theorist didn't just mimic the human proofs that Whitehead and Russell had published. For one of those theorems, the machine actually found a proof that was more elegant.
Yeah, that's the real kicker.
Like, it required fewer steps and was more logically beautiful than the proof provided by two of the greatest minds of the 20th century.
It totally outlogiced its human masters. It found a cleaner, purely mechanical path to the truth. And the funny thing is, the creators actually had trouble getting those results published in human mathematics journals at first.
You were probably defensive.
Oh, almost certainly. But that success deeply impacted how those scientists viewed the future. I mean, by 1958, Newell, Shaw, and Simon published a paper containing a quote that is just dripping with audacity.
Let's hear it.
They wrote, and I quote, "There are now in the world machines that think, that learn, and that create. Moreover, their ability to do these things is going to increase rapidly until the range of problems they can handle will be coextensive with the range to which the human mind has been applied."
Wow. They were essentially calling their shot in 1958, predicting the entire future of AI based on this one breakthrough.
They completely saw the horizon.
But, here's where it gets really interesting for me, though. I have to push back a little on what this machine is actually doing.
Okay, go for it.
Aren't these early programs, and I mean even the modern ones, aren't they just glorified calculators? Like, how does a program actually prove a philosophical or mathematical concept without just crunching numbers really fast?
That's a great question, and the distinction really lies in the difference between arithmetic and formal logic. A calculator takes numerical inputs and runs them through a hardwired arithmetic operation. It just computes.
Right. Numbers in, numbers out.
Exactly. But automated reasoning systems manipulate symbols. They take abstract logical concepts and apply a strict set of rules to transform those symbols into a verified truth. They don't just calculate a result, they generate the actual chain of reasoning.
Okay, so if I am a computer scientist trying to build one of these logic engines, what kind of programming language am I even using to talk to the machine? Like, it can't just be standard code.
No. You are using highly specialized languages designed specifically for symbolic manipulation. Let's look at a major system from the sources. the Boyer-Moore theorem prover, also known as NQTHM.
NQTHM. Got it.
This started in 1971 in Edinburgh, and it was built entirely in pure Lisp, which is a very unique, highly recursive programming language.
Okay.
And NQTHM had this fascinating mechanism for learning. It utilized an induction heuristic based entirely on the failure of its own symbolic evaluations.
Yet how does a machine logically learn from a failure?
Well, imagine the system is trying to prove a rule that applies to all number. It tries to calculate the steps normally, but it hits a wall where a variable is unknown and it just can't proceed.
Like a dead end.
Right. Now, a
Okay.
normal program would just crash or throw an error, but NQTHM was designed to analyze the shape of that dead end.
The shape of it.
Yeah, it looked at the exact point where the evaluation failed, and it used the structure of that failure to guess the underlying mathematical pattern, formulating a totally new logical step to bypass the wall.
Oh, wow. So it literally mapped its own dead ends to find the open door.
Exactly.
That is brilliant. But let's bring this into the real world for a second, because if we're talking about trusting software to, I don't know, fly a commercial airplane or manage a national power grid, we can't just have a system making good guesses. We need absolute certainty.
Which is exactly where a system like ROC comes in.
ROC, spelled R-O-C-Q. Right.
Yes, formerly known as COC. This system was developed in France and represents just a massive leap forward. ROC operates on something called the Calculus of Inductive Constructions, or CIC.
Okay, see, I see.
In the CIC framework, a mathematical proof and a computer program are treated as the exact same mathematical object.
Wait, hold on. A proof and a program are the same thing.
In this specific architecture, yes. And because of this, ROC can do something incredible. Let's say you write a logical specification proving mathematically that a specific sorting algorithm is flawless.
Okay.
ROC doesn't just give you a check mark saying your math is right. It mechanically extracts that theoretical proof and translates it directly into actual executable source code like OCaml or Haskell.
Are you serious? So you do the pure math and the system literally spits out the working software.
Yes. And because the software was extracted mechanically from a formal logical proof, it is physically impossible for that resulting code to have a logical bug.
Right.
It is strictly guaranteed to behave exactly as specified.
That completely blows my mind. What is the limit to this then? Like, how complex of a problem can these systems actually handle?
The milestones are pretty staggering, honestly. Back in 1986, a researcher named Natarajan Shankar used the Boyer-Moore system we talked about to formalize Gödel's first incompleteness theorem.
Which is huge.
Massive. And by 2004, the ROC system was used to verify the four-color theorem. But one of the most wild examples from the sources happened in 2016 regarding the Boolean Pythagorean triples problem. Researchers formalized this as a Boolean satisfiability problem, or a SAT problem.
I saw the term SAT problem in the reading. What actually is that?
Basically, a SAT problem asks if there is any possible way to assign true or false to a massive set of variables so that the entire overall equation evaluates to true.
Okay, true or false logic dates.
Right. For the Pythagorean problem, imagine you have to color every whole number either red or blue. The rule is that no three numbers that satisfy the Pythagorean theorem, like 3, 4, and 5, can all be the same color.
Okay, false.
So mathematicians wanted to know if you could color numbers this way forever without breaking the rule.
And how did the automated reasoner tackle that?
By using pure brute force logic combined with some really smart pruning techniques, the system checked combinations all the way up to the number 7,824 and proved that, yes, you can color them without breaking the rule. But at the number 7,825, it becomes mathematically impossible. And to prove this, the system generated a proof file that was 200 terabytes in size.
200 terabytes.
Yeah,
No human being could ever read that proof in a single lifetime.
not even close. But we trust the result because we mathematically trust the logic engine that generated it.
But wait, if we had the logic theorists outperforming humans back in 1956, and we are generating 200 terabyte proofs today, why hasn't automated reasoning just been the dominant force in tech for the last 70 years? I mean, the reality of technological progress is rarely a straight line. What happened in between?
Yeah, it definitely wasn't a straight line. The field actually hit a massive wall in the 1980s and early 1990s. This period is widely known as the AI winter.
Right, the AI winter.
The theoretical math was totally sound, but the hardware simply couldn't handle the combinatorial explosion of data required to run these proofs at scale. Funding dried up.
So they just got stuck waiting for better computers.
Pretty much. But the researchers didn't stop. They basically went into hibernation and optimized their logic engines. And the rebound became highly visible by 2005. That's when Microsoft started integrating automated verification technology directly into their internal projects.
Oh, interesting.
Yeah, they even incorporated logical checking into the 2012 version of Visual C. So the technology moved out of academic labs and straight into the software compiling tools used by millions of regular developers.
So what does this all mean for us today, right in the middle of this massive boom in generative AI?
Well, in the 2020s, the focus has violently shifted back to automated reasoning as the ultimate cure for the AI hallucination problem we talked about at the start.
Bringing it full circle.
Exactly. Large language models guess the next word based on statistical patterns. They don't actually understand truth. So to fix this, researchers are building reasoning language models like DeepSeek R1, which are designed to literally spend additional computational time pondering a problem before they generate a single word of output.
But how does spending more time pondering actually fix the hallucination fundamentally? Like, isn't it just thinking about a wrong answer longer?
If we connect this to the bigger picture, it leads us to the absolute bleeding edge of the field: neurosymbolic architectures. This is the marriage of two completely different eras of computer science.
Okay, neurosymbolic. So the neural part being the modern neural networks and the symbolic part being the formal logic engines like ROC that we just discussed.
You nailed it.
It sounds kind of like pairing a wildly creative architect who dreams up impossible, gravity-defying buildings with a ruthless safety inspector who checks the math on every single load-bearing beam before a single brick is laid.
That is a perfect way to look at it. The neural network provides the intuition, the pattern recognition, and those creative leaps. It drafts the blueprint.
Right.
But before that answer is ever shown to you, the symbolic logic engine takes over. It attempts to formally prove the neural network's generated answer using strict mathematical axioms.
And if it fails?
If the safety inspector finds a logical flaw, it rejects the answer and forces the neural network to try again. The entire goal is to give AI a built-in, mathematically flawless lie detector.
Man, it really is the invisible safety net for our modern digital infrastructure.
Yeah.
Because as we discussed, we are handing over control of power grids, financial markets, and aviation software to machines.
Yeah.
If there is a logical bug in those systems, the consequences are just catastrophic.
Absolutely. And to keep improving that safety net, the community maintains this massive, constantly updated library called the TPTP, the Thousands of Problems for Theorem Provers.
Library of problems.
Yeah, it provides a standardized battleground for these systems. There are even regular competitions held at the KD conference where different automated theorem provers from all around the world compete to see which system can solve the most complex logic puzzles from the TPTP library.
It is literally the Olympics for artificial logic.
It really is.
I love that so much. An international competition to build a sharper, faster truth machine. As we wrap up this deep dive, I want to turn it over to you for the final word. Looking at this entire journey from the 1950s to today, what is the biggest takeaway that listeners should be chewing on?
You know, I keep going back to that initial shock in 1956 with the logic theorist.
Yeah, that was wild.
The machine found a more elegant mathematical proof than Whitehead and Russell, and it did it by mechanically applying logical rules without using a single drop of human intuition.
Right.
If a machine can create a more elegant truth through sheer mechanical deduction, it really forces us to ask a rather uncomfortable question.
Which is?
Is human intuition actually the magical, irreplaceable source of creativity we think it is? Or is intuition just a biological shortcut, a messy adaptation our brains use simply because we lack the processing power to run the formal logic?
Our greatest aha moments just workarounds for our biological hardware limits.
That is a wild thought to leave on. Thank you so much for joining us on this journey into the invisible logic running our world. Keep questioning your own assumptions. Keep checking those ice crystals. We will catch you on the next deep dive.